Hi everyone and welcome to another PAT Problems video. My name's Helena and I'm the Access and Outreach Manager for the Department of Materials at the University of Oxford, and today we're going to be taking a look at question number 14 from the 2016 PAT paper. So this question is concerning circular orbits. So here we're asked to assume that the moons Io and Europa travel in circular orbits around Jupiter. The radius of Europa's orbit is 1.6 times that of Io's. In what ratio are the moon's orbital periods to two significant figures? Okay, so what are we told in the question? We're told that the radius of Europa's orbit, RE, is 1.6 times the radius of Io. Okay, and we want to find the ratio of the orbital period, so TE to TI ratio, or as a fraction, TE over TI. That's another way we can write that ratio there. Okay, so first things first with this, let's consider the forces. Now you might remember this relationship, but I'm going to talk it through from sort of first principles. So thinking about the forces that are acting during this circular orbit, you have the force towards the center of the orbit due to that circular motion, which is mv squared over r. And for a stable circular orbit, that's balanced by the gravitational force acting between the two objects. So G mm over r squared. Okay, again, you might remember that, but I like to think about it from first principles in order to derive it. Now let's think about the orbital period of these orbits. So T, well, that's a simple, speed distance time relationship going around a circle. So our orbital period T is equal to the distance divided by the speed of the orbit, otherwise known as the circumference of the circle, so 2 pi r, divided by v. Okay. So what have we got in these equations? Well, we've got relationships between the masses, between g, between r, but we don't want the v here. So let's rearrange this equation here to make v the subject and substitute that into that first equation. So if we do that, we have that v is equal to 2 pi r over t, and let's substitute that in to that equation there. So I'm going to write this like this. So we have m over r, 2 pi r over t all squared, which is equal to g over r squared. So our lowercase m's cancel here. I'm now going to expand this bracket. Actually, I'm also going to cancel one of the r's on the bottom there, so we make it a little bit simpler. So here we now have 4 pi squared r squared over t squared is equal to g over r. Okay, I'm now going to move this r over the top here to give us an r cubed. And I'm also going to take this term here, this constant, over to this side here. So we're left with something that looks like r cubed over t squared is equal to g over 4 pi. Now this is a constant for whatever system we're looking at. So I'm just going to write that as a constant k, which means we now have a relationship between the radii and the orbital periods being a constant. So this means that for any set of orbits, this relationship here is going to be the same for any other orbit, any other circular orbit as well. So thinking about our two moons, we have that r e cubed over t e squared is equal to ri cubed over t I squared. So that relationship is the same for both orbits because it's equal to this constant. So now we can rearrange it to get that fraction that we wanted at the start. So I'm going to do that here. So we have te squared over ti squared, so moving that up here essentially, is equal to re cubed over ri cubed. Let's substitute in our relationship here for re. So that's equal to 1.6 times ri all cubed divided by ri cubed. The ri's cancel, so we just get a value for te squared over ti squared is equal to 1.6 cubed. Now let's square root this to get the value for te over ti, which is the ratio that we want, which is the same as 1.6 to the power 3 over 2, which, if we pop that into our calculators, gives us an approximate value of 2.0 to 2 significant figures. So that is our answer there. So that's the way I go about solving this problem. As with the other questions that we focus on in this series, this is one that could translate nicely into a multiple choice question given the current format of the PAT. And like I say, this is my way of solving this question. I hope that was useful for you to see. And please join us again for another PAT Problems video.